Okay, so who has actually tried to make their package or software reproducible? Okay, that's actually more than I expected, so I'm happy to see that. Okay, so let's talk about what are reproducible builds. The point of a reproducible build is if I give you my source code, or my sources in general, that would be images, XML files, or just actual source code, and you build it, and I build it, that we get the same exact bit-by-bit identical result. Okay? We'll talk about why that matters in a bit, but by that we make two little distinctions. Just a sec, this is uncomfortable. We make bit-identical output and same content after post-build filter applications. So what does that mean? So bit-identical output is really simple. If you're building for something like a Linux distribution, for example, or maybe if you're a Java developer, you end up with a jar file or an RPM file or a deb file. So if we both take that deb or RPM file and compare it, we should have bit-by-bit identity. So if we make a hash, it should be the same. So that's the one that we strive to do with reproducible builds. It's the easiest to check. We also have same content. So a lot of things like archives, for example, jar archives put some metadata in there. And sometimes people don't want to, in the upstream project, fix that. What we can do as maintainers is have build compare, that's a package, and write filters that specifically take out the bit that is unreproducible, that we know is unreproducible. So we can say, okay, a bit is not reproducible. Okay, this is to work less and less. Okay, so we can say this is not reproducible, but we can guarantee that everything else is reproducible. So that's less desired because we have to do more work as maintainers to actually build the packages and make sure they're reproducible. And when the upstream changes things, we have to fix our filters. So now, I don't know how many of you have done, Linux type development where you're packaging packages for the masses, and it's not just an exe download. But this is somewhat how a life of a binary goes, right? So this is the process from source code to you running it on your machine. So we have a developer who pushes his changes to Git. At some point, when he's happy with the state of the code, he decides, okay, it's time for a new release. He creates a release. Typically, this is done with tarballs nowadays, still. Because of this, the tarballs, we're going to discuss that a bit in the future. The XZ hack actually changed the perspective on tarballs. We try to avoid using them nowadays, but most infrastructure still relies on tarballs. So the tarball is on the upstream. If you go on GitHub, for example, for a package and you have releases, there's a tarball there. A package maintainer for a distribution of choice, be that an open distribution like Debian, OpenSUSE, or Arch, or an enterprise distribution like Red Hat, will take that upstream tarball. He will create a package. For the package, it depends on the distribution, but for example, for OpenSUSE or let's say Red Hat-based or RPM-based distributions, write a spec file and use their build server to actually make sure that the package is built in a way that complies with that distribution's practices. So binaries have to be put in a certain place. Desktop files have to be put in a certain place. SE Linux, AppArmor profiles have to be written. This is all work that's done by packagers and usually not by the upstream maintainers. The packager then, once he's happy with the package and it gets accepted, or it's just an update and the update is proved and the tests run and everything's good, the build server will then start building this package. And after it's built, it will distribute it to the seed mirrors, which will then distribute it to the mirrors that people host either as volunteers or as companies. And the mirror is where you will download your package from. So when you go into your, I don't know, you say apt install, and you pick a package, it goes to a mirror, finds the package, downloads it, and you get that binary, right? So this is the current supply chain of source to binary. And in most of these steps, we already have existing solutions that we use or we can use to protect the integrity of the code, right? So the developer can sign his commits before he pushes them on Git, okay? So you can do a digital signature, the commit is signed, and if he's meticulous about it, if there is an unsigned commit, we can see, oh, that's out of the ordinary, what's going on, and we can find out a bad actor. So after he's done and decides that, okay, now I have a release, he can make a tarball and he can sign the tarball, okay? And if he's really meticulous, he's gonna check that the tarball actually still has the same contents that he expected it to, because it could have been changed and he could have signed a tarball that he didn't intend to sign. And then the packager can check that signature of the tarball, create his build, and the build server can build the binary. And then the build server, once it's built, typically will also sign the binary. So every distribution signs the binary, so that when you download from a mirror, you don't need to trust the mirror, because the mirror will serve you a file, but your package manager checks the signature of that package, and if it doesn't match, it'll alert you and tell you, hey, do you really want to install this? And you probably shouldn't. So where in this step here is there a hole in trust? Anyone? Build server. Okay, so we implicitly trust that the build server is taking that code that is signed and verified and actually using it to produce the binary that we expect. And this is a false trust. It has also been misused in a very large-scale attack a few years ago. Can anyone name it? It was the SolarWinds attack. I'm sure most of you are familiar with it. So the SolarWinds build server got breached, and the attackers actually changed the code that was being built and also stole the signing keys, so that the executable that you got was officially signed by them, and no one batted an eye. So this is the problem that reproducible builds tries to solve, right? Because it tries to move away the trust from the build server, because you can always take the source and just rebuild it and check if the build that you get is the same as the build that is given to you by the build server that your distribution or your packager is providing you with. So now you no longer have to trust the build server, which is great, because now there's one less step that can go wrong. Right now, build servers are, you need to keep them very secure, because if someone breaches, for example, Red Hat's build servers and changes something, like with the XZ attack, which was done, they can change what the output binary will be, and it's very hard to notice. Unless the actions that the binary takes are very obvious, it's very hard to know that, okay, the binary has changed and didn't actually come from the source code that we meant it to. So I kind of already started on this, but these are the main points of why you should care, because it creates an independently verifiable path. So that's what I just spoke about. You can be sure that the binary actually resulted from the code that the upstream maintainer created. It protects your build infrastructure, or rather, you don't have to trust it anymore. And this might be for you who care about digital sovereignty and privacy. If you have an open source software, well, you can read the source, but you just download the binaries from their website. Are you really sure that the binaries did result from that source? You're not, right? Unless they're reproducible and you can check. Or you compile it yourself, which is often a hassle for people, and they choose not to. So that's why reproducibility is important, because we can make automatic services that do that for us. They will automatically check the sources and rebuild, and Arch Linux, for example, has this. It's called rebuilderd. It will automatically rebuild packages and flag if something changes. There's also the whole works on my machine aspect. If we have a reproducible build, we will always get the same binary. So if you and me compile it, we should get the same binary, and it should function the same, bar some CPU differences maybe. There's also discovery of obscure bugs. So a lot of bugs have actually been discovered by this. You'll see a list later on the reproducible builds webpage. You can check it out. That have been found because of people caring about reproducible builds. A lot of these bugs result from race conditions in the build process. Some of them are straight up corruption because the build tools had, for example, uninitialized memory, or you were using memory that they weren't intending to use. And that resulted in build time corruption, which didn't result in the binary not working, but it could have had an issue in some specific scenarios. So let's say I convinced you, and now you care about reproducible builds. How do you go about fixing unreproducibility in your code base? So these are top things that cause unreproducibility. It's not by no means an exhaustive list. The exhaustive list is on the website, and even that one's probably not exhaustive. These are just the most common scenarios of why things become unreproducible. So the most common file system in Linux ext4, for example, has random file system ordering. This is fixed by distributions. They patch the ext4 file system on the build service to have a constant random seed, and therefore you don't have a file system ordering. So if you use an established build service like Open Build Service, this is taken care of for you. And then there's compile time CPU detection. So let's say you are a C programmer or a C++ programmer or Rust, whatever compiled language. If you build with mnative flag, your compiler will optimize the binary for your specific CPU features, right? So if you have AVX extensions, it'll use AVX, and if you don't, it won't. Of course, this will result in different binaries. If I build it on a different processor than you, the binary will differ. In most Linux distributions, we don't use compile time CPU detection because we can't make guesses on what kind of CPU you might have, right? We can't build with AVX and then you download the binary and you get an illegal instruction fault and it won't run. So typically they pick a lowest common denominator that they decide to support and they support it. However, for high performance computing, this remains an issue because that 10–15% that you might get with compile time CPU detection is important to you, especially when you're paying a lot for electricity. And in that cases, a lot of upstream projects decide to ignore the use of reproducible builds. If you are such an upstream project, I would advise that you make another make target that is reproducible and one that isn't. And then people that need that extra speed can compile it themselves as they already do anyway. Archive metadata, so tar, that image over there is the tar header. You can see in the top, I don't know if you can read it, but it stores name, file mode, owner ID, group ID, file size, and checksums, and last modification dates, and things like that. It also stores the process ID of the tar process that created the tar archive. I don't know why. No one really knows that I talked to about reproducible builds, but if you are making a tar in your build, there is about 100-character long command line that you have to use to force tar to be reproducible. So it creeps up in a lot of places. The same goes for jar. So if you're a JVM or a Java developer, JVM makes class files reproducibly, that's fine. But when it packages it into a jar, it puts in a lot of metadata, and that isn't reproducible. Even if you fix that, you can fix it with default flags. If you fix that, some people then sign the jar, and that signature isn't reproducible. So you should do the Linux way of signatures, where you make a hash and you sign that hash. Okay, so that's the reproducible way to do a signature. Don't embed it into files. Right? Don't do a signed exe or a signed jar. That just causes unreproducibility. Another really cool one, but doesn't apply to most things, is ASLR. So in 80% of software, you run GCC or you run your compiler, you get an output, and that's it. But the 20% of projects, something like Emacs, for example, have an entire build chain where something is first built as a binary, and then that binary builds further binaries. Now, if that binary has memory issues, like uninitialized memory, and it's running on an ASLR-enabled system, which all of them are, you will get random bytes in your output. Now, that this might or might not affect your runtime, but it will certainly produce unreproducibility. There is a lot of cases of this that was caught in the wild. Some of them were then actually discovered to be security vulnerabilities, caught because people cared about reproducibility. And we'll actually talk about this one as an example. We'll show you an example of how it can come about and how we can fix it. And we'll show some tools. And of course, people really like to, for some reason, put random calls in their build environments. So they'll make a random for the file name, or they will put timestamps into their resulting build, which of course aren't reproducible. For timestamps, there is that source date epoch. This is an agreed upon environment variable that you should use if you want to use timestamps in your build, because then the build environment can override it, and we can, again, have a reproducible build, and you can still have your timestamps. Okay, so now let's move on to examples. Oh, by the way, before I do, reproduciblebuilds.org is the page where you can learn more about this if you do care. There are some very big projects that use it. Python, for example, has reproducible tarballs, but it doesn't really run reproducibly. The binary builds aren't greatly reproducible due to performance reasons. If you care more about that, you can ask me later. for OpenSUSE specifically, but it's a really good starting point because OpenSUSE has a very accessible build service. You can check out this package, the unreproducible package. This is the example we'll be showing today. It's a selection of the most common ways unreproducibility creeps up, and you can try and fix it yourself to learn about reproducibility. And I'm sorry. And reproducible OpenSUSE. So this is the tooling for actually testing reproducibility of your packages. Now, most major distros have one. Arch is also striving to be very reproducible. Debian is also striving very hard, and most of them are above 80%. So Arch is about 83 or 85. OpenSUSE is like 95% reproducible, and Debian is pretty high there as well. And they all have their own infrastructure to test for reproducibility. Fedora is now also trying to use Arch's Rebuilder D service. So now let's go on to example. This is the tooling if you would decide to use it, and this is the tooling I'll be using right now. So this is the example we'll be looking at. This is meant to present a program that is used in the build process, right? So this is not the build that we're building. It's a program that will then be used in the build process. If you care, here is the make file. So it'll build 1.c, run it, and the output of 1.c is our build. Can you spot what would make this unreproducible? Oh, sorry. Better? Shamo? Yeah? Can you spot what would make it unreproducible? This one's sneaky. No? Huh? Nope. The what? Which one? This? So that's unassigned, but then we assigned data 1 and data 2. Okay? But it's close. Very close. Yeah? The what? NDNS, no. No. Well, it would be if we were comparing builds for different NDN targets, but let's assume we're comparing for x86, 64. So the order should be the same, but you're also very close. It is about the struct and memory. So the struct, the character and short aren't big enough to have the full pad of the struct. It doesn't fit, it's not aligned. So what the compiler will do is it will pad the struct to make it aligned, okay? And that padding, those bytes, if you have ASLR enabled, if you don't know what ASLR is, it randomizes the address space at runtime. If you have ASLR enabled, those bytes will be random. So it's actually super easy to test for. If you suspect that ASLR might be causing, just disable ASLR in your build environment, run it again. If it's reproducible, go find the error why, because somewhere you have a memory issue somewhere, right? But it's an easy way to test, but it's not the fix. So how would we fix this? If just to make it a bit more clear, there's some more bytes here that are random, because of ASLR. So how would we fix this? Yeah, exactly. Mem set it to 0. So I have a patch here that I prepared. It's very simple. You just mem set that to 0. You don't really need to see the full thing, but you just mem set it to 0. So if you intend to use this, I need to speed up. If you intend to use this, there is a spec file in here. If you want to play around with the unreproducible package, you open this spec file and you scroll down here to build. You CD into the package that you want to try. So there's ASLR, there's compile time checks, there's floating point issues, there's timestamps. You CD into the one you want to check. And then, assuming you installed the OpenSUSE reproducible build tools, you have a command called RBK. So RBK will run the OpenSUSE build environment. It will spawn a KVM VM, and the entire build happens in a VM, so you don't really have to worry about destroying your system. And it'll build it twice, and it'll compare. It'll make sure that the output, if the output is identical or not, it'll let you know. It's decently fast for this small package. And then we'll apply the patches and see the change. Let's give it some beans. Okay, so you don't have to do that. That it would mount the build environment. You can just ignore that sudo. But here we can see, okay, we have a differing of package, and it compares everything. So it compares RPM tags, it opens the RPM, it checks the inside of the RPM, the files. And here you can see, okay, the file out ASLR differed here. And you can see the hex dump. Can you see it, by the way, or do I need to increase the size? Increase the size, okay. Okay, so right here you can see, okay, the out/ASLR file differed here. And now I'm just gonna apply the patches that I pre-configured. So if you apply the patches, you just rerun the build, and we should see that that's changed. So this build still won't be completely reproducible. There is an RPM tag issue, but we will see that the package content is no longer differing. Okay, so we can see there is still differing, but the package content is identical. So the actual files inside are identical, but because this is smart, it actually unpacks it and checks the RPM headers and tags separately from the actual content of the RPM. It doesn't just do a hash on the RPM. So now we kind of fixed partly this package. So I invite you to go ahead and try this yourself. Packaging for Linux is a pretty fun experience. And if you do package, you can actually try and check if the package is reproducible by just running the rbk command like this. If you just run that, it'll tell you, hey, is this package currently reproducible or not? Okay? And again, 20% of the work is for 80% of the packages. 80% of the packages are basically reproducible by themselves. It's only the special ones that have very complicated build systems or build environments that have issues. So, because we're running out of time, let's go ahead and forward. We'll not tackle the timestamp one as well. So what the future holds, the whole idea of this is to integrate package managers with reproducible builds. So that when you query and try to install a package, it takes that binary, checks its checksum, and then queries a separate independent server that rebuilt the package. And that server will tell it, okay, this binary is what you would expect from the source code. And this can protect us from compromised build servers or mirrors. So if someone compromises OpenSUSE's build server and creates a malicious package and signs it with the key, and it distributes it, and I try to pull it, an independent reproducible server will compile it, will tell me this is wrong, it doesn't match the source code, and I can decide to, okay, I don't want to take the risk, ignore it, don't install it. So of course we want to try to get to 100% of reproducibility on all packages. This will never happen because some upstream packages will just say no, they don't care. For example, in Python, glob isn't ordered because it's 10% faster, and they don't want to change it. They will never change it, so whatever uses glob will not be reproducible like that without any patches. But if we can get to a high 90% and mark the packages that aren't reproducible as unreproducible, then that's already a great success. And there's also a website that I would mention. You can put in whatever package you want, and it'll tell you for, I think, ArchDebian and OpenSUSE if that package is currently reproducible or not. So here's some statistics from Arch Linux. These are from last month, the current reproducibility state, and also for OpenSUSE. So for OpenSUSE, we have about 16,000 packages, and about 15,400 or 500 of them are reproducible bit by bit, so without filters. So it's actually in a pretty good state in terms of reproducibility. So the holy grail that we want to get to for reproducibility is this, for software deliverance. So we already do code signing, if you care, and we also sign the releases. What we want to do is move away from tars to git tags, because the way that the exit attack worked is they sneaked in some files that weren't in the source into the tarball, which then attacked the build server. So if we move away from tarballs and just do git tags, we can circumvent that, and it'll give us a lot clearer view into the source code that we're actually compiling. From that, it's nice to have a trusted build infrastructure, right? Because at the end of the day, it's fast if you just sign it, and that's the first thing you check the signature. But reproducible builds also really ties it in together, because with reproducible builds, as I mentioned now, you don't have to trust the build infra. So at the back there, you'll see the binary signing, which has been the golden standard in software distribution since Microsoft decided they want to be big. And we have seen it fail over and over and over again. We have seen it fail with SolarWinds. We have seen it fail with stolen signing keys from legitimate companies that were used to sign malicious either drivers or malicious executables. So we know that binary signing by itself, it's fine, but it's not the holy grail. It doesn't protect us as well as we would hope. And reproducible builds fixes that. Now, a lot of you might be proprietary developers and your code isn't open source. So you might be saying to yourself, I don't care about reproducible builds because I can't open my source anyway. There is companies that will do reproducible builds for you. And Microsoft, by the way, does this, and SolarWinds also does this since that hack. That was the first thing they decided to do after the hack. You can pay a company, sign an NDA, give them your source, give them constant access to your source, and they will constantly rebuild your package and compare it to the package that you're distributing. So the executable, or however you're distributing it, or if it's a Docker image, they'll constantly compare it and make sure that it's the same, and you can have fast alerting if you decide to distribute something that didn't resolve from your sources. CrowdStrike probably could have been saved by this. If either the client checked independent servers before deciding to use that file that it pulled, or someone else had distribution checking and alerted them that, hey, your file that you pushed didn't result from your sources, they probably could have avoided a big mess. So just quickly, there's a few arguments that people have against. One, it takes a lot of effort. True for the 20 to 15% of the packages, everything else is pretty much free. And speed, so I already discussed this. You can have an effect on speed, but if you care that much, compile it yourself, do some mnative, and that's it. And again, closed source software, but you can, in fact, do it with closed source software. It's just a bit harder, and you lose some of the benefits like the privacy and trust in the source that's executing. By the way, if you do profile-guided optimizations with C or GCC, you can also do that. You just need to make sure that your input is constantly the same. So you can't random, it can be random, it just needs to be reproducible random. Okay, and then the profile-guided optimization will result in a reproducible binary. So that's it. I would like to thank Bernard M. Wiedemann for his dedication on reproducible builds. He's the person really pushing it hard at SUSE and OpenSUSE as well, and does a lot of work by himself. And for my friends at pva.sc for maintaining infrastructure, used to host the Arch Rebuilder service. It's actually up there in the server room, and thank you to Free for providing the hosting and internet necessary. And that's it. Thank you very much.